So hello, I will continue to share another study on the Sacramento Shade Program, but this time based on the 22-year monitoring from 1991 to 2013. So this project was a collaborative project with other researchers like myself and Junab Lee from UT Arlington and the Forest Service researchers, Greg McPherson and Lara Roman, our previous presenter. So as seen in the previous presentation, it is essential to monitor how planted trees actually survive over time in order to accurately model and ensure the projected benefits that the tree planting programs intend to provide, especially in the long term. But many tree planting campaigns are too new to provide empirical evidence of how planted trees actually survive, grow, and perform in the long term. So in this sense, studying the Sacramento Shade Program as the longest operating and the largest utility-sponsored tree planting initiative in the U.S. provides a valuable opportunity to provide empirical evidence and make implications for other recent tree planting programs. So this 22-year study was possible because we could access the early monitoring data on the planting program trees from early 1990s, which was used in these two initial studies published in 1998. And based on the mortality and the growth assumptions, these two studies projected the energy-saving performance of the Sacramento shade trees over 30 years. And these two studies made a quite different assumptions. If you look at their mortality assumption, for example, the Simpson and McPherson made us assume that tree death and removal would be approximately balanced by tree growth and replacement. And if you look at the other study from Smart, Hildebrandt, and Zarkovich, made an assumption based on the survivability. So assuming that 58-70% of the trees that were distributed would survive after 30 years. So in our study, we aim to answer three research questions. So first, how many of the shade trees planted between 1991 and 1993 were alive in 2013? And secondly, how large did they grow? And third, how are their effects on the cooling energy use, and how do our findings differ from the initial projections? So to answer those research questions, we randomly selected and visited 19 true properties from the original 254 properties that were included in the initial study by Simpson and McPherson. So these properties are across the Sacramento County. And then since the initial planting from 1991 to 1993, we collected the tree survivor and growth data from the two field surveys. The first survey was done by the SMUD staff in 1994 to check the early establishment status, and then the second survey was done by the authors in 2013. And to document longitudinal survivorship, we also used the aerial photo interpretation to track the individual trees between those two observations. So to answer our first question on the survivorship, we used the survivor analysis, the same method that Laura used in the previous 5-year study, and based on the survivor status from the field surveys and aerial photo interpretation. So for example, if a particular tree was found on the aerial photo in 2011 and but was not found in 2013 field survey, then we could assume that the tree was removed between 2011 and 2013. And for the second research question on the growth attainment, we compared the actual tree sizes measured in 2013 to the projected tree sizes 30 years after planting, so that was used in the initial study from Simpson and McPherson. And so they grouped the species into 5 tree classes based on their mature tree size, small, medium, large, and the growth rate, moderate growth or rapidly growth, and then projected their sizes by tree classes. And finally, for the energy performance, we used our measured survivor and growth data and then put it into SPS and the MicroPulse, which was the same modeling programs used by Simpson and McPherson. So we intentionally used this program to avoid any kinds of variation in our energy simulation results by using different energy software. So this diagram shows the overall picture of the program tree survivor over 22 years in Sacramento. So out of 317 trees that were distributed in 1991 and 1993, about 13% were found missing or not planted at the first visit in 1994. And then about 12% were found standing dead, and about 88% were alive in 1994. And among those 1994 survivors, about 46% were found to be alive in 2013. So, and we compared these results with the initial mortality assumptions. So first, Simpson and McPherson assumed that in our field, tree death and removal would be balanced by tree growth and replacement. But what we found was that in 2013, only about 27% were seem to have been replaced by younger trees in the same locations as planted, and those replacements were much smaller than their projected mature size. And then the Hildebrand and Zarkovich used the survivability concept, and then they assumed the 58 to 70% survivability. But what we found was when we converted our survivorship into survivability, ours was 35%, which was much lower than the initial projection. And so this survivor curve is the 22-year post-planting survivorship, and which was 42.4%. And we cannot make any judgment on whether it was a high survivor or low survival because there's no other monitoring data on yard trees on over 20 years. But when we compare these results with the initial assumptions from previous studies, it was substantially lower. And the survivorship was also significantly different among different tree classes. So overall, the medium-sized trees with spreading crowns show the highest survivorship, and as opposed to the smaller-sized trees shows the lowest survivorship over the study period. And when comparing the projected tree size to the measured tree size, the average growth attainment ratio was 75% for the tree height and then 69% for the crown diameters across all tree classes overall. And given the fact that the projected tree size was for 30-year-old trees and our measured trees were 20 to 22 years old, so these results show that actual and predicted growth rates could be somewhat consistent. And the attainment ratio were largest for the medium-sized trees, again, with upright crowns, and then the lowest for the small-sized trees. And lastly, for the energy saving performance, our simulated energy annual cooling energy savings per property was 107 kilowatt hour, which was about 1/4 of the initial projected savings. And it's primarily because tree survivor was much lower than the initial assumptions. And in 1994 survey, we found an average of 3.1 trees survived, observed in the property, but in 2013, we saw on average about 1.3 trees alive. And the energy saving per tree was 80 kilowatt hour, which was about half of the project energy saving. But we should note that here again, we compare the 30-year growth projection with a 22-year estimate, so energy saving trees grow. And if we compared our per tree energy saving with other studies in Sacramento, our 80 kilowatt hour saving per tree was similar to the recent results reported by Donovan and Buttrey, which was based on the observed energy saving from the tree cover in Sacramento residential areas. And these results also suggest that the early simulation studies from 1990s made quite optimistic assumptions on their tree survival. And we also examined the biophysical and socioeconomic factors associated with this 22-year tree survival. And then in the establishment phase, we found higher mortality was associated with properties with a greater number of trees delivered, which means that properties that ordered too many trees was associated with high mortality, possibly because the residents' tree care for an individual tree is reduced. And also, we found that trees planted in the front yard survived better than those in backyards, perhaps because residents take care of their front yard more than backyard because they think the front yard as a showcase to neighbors, according to other literature. And we also found interesting results that the net property values, the properties with low net property value and the high net property values were associated with higher tree mortality compared to those with medium net property values. And our regression results doesn't tell why, but we could assume that there is a different ecological dynamics between those two low and high net property value that affect the tree survival. And the overall, the mature tree size and the homeownership stability were influential. So the species with the small size trees, including like Japanese maple or crepe myrtle, had a lowest survivor. And again, the properties with very unstable home ownership, like as you saw from the Lara study, showed a lower survival rate. So in conclusion, this study has 5 key takeaways and implications for urban greening and planning. And first, these studies show that trees do save energy. So this study and the Donovan and Buttrey from 2009 concur that a tree in Sacramento saves around 80 kilowatt hour per year. But trees save more energy when they survive longer. So we found that lower energy saving performance. We found the lower energy saving performance than the initial projection because of mainly due to the higher mortality rate. Therefore, increasing survivorship is the key for increasing performance of the planted trees. So there are several ways that we can increase the survivorship. So for example, based on our results, the increasing medium mature sized trees or rapidly growing large trees would help achieve higher energy saving performance because of their higher survivorship as well as the larger tree canopy cover that gives larger shade over time. And also preparing the new challenges like droughts in case of California through smart landscaping guidances would be helpful as well. For example, the California's relief campaign, Save Our Water and Our Trees, provide a simple tree care guidances to protect trees from impact of droughts. And also, outreach through emails and mails and phone calls to remind the residents to engage in proper tree care may be helpful as well, because again, yarley trees are heavily influenced by the residents' tree care. And the Sacramento Tree Foundation, as Laura mentioned in the earlier presentation, has already started doing a systematic phone calls and emails to the customers. After the 5-year study, Laura's 5-year study reported that a few residents practiced the good tree maintenance. And fourth, monitoring long-term survival and growth that provides the empirical evidence would be really critical for the data-driven urban forest planning and management. And this kind of monitoring for survival and growth may give some harsh realities about the tree performance, but we really appreciate the Sacramento Shade Tree Program's dedication to collaborating with researchers to study this issue, because many tree planting programs plant trees, which is great, but few of them are actually monitored after. So, and finally, understanding the social-ecological dynamics that affect the tree survival growth are very important. So incorporating those understanding on the socio-economic dynamics, long-range and strategic tree planting as a green infrastructure planning would be imperative for mitigating and adapting to climate change. So that's it, and then we appreciate the funding from the U.S. Forest Service and Tree Fund, and the students from UTA and UC Berkeley, and the folks from UC Berkeley, and the Sacramento Tree Foundation and SMART. Thank you.